Welcome to the Explainer. Today we're going to tackle a real classic from Irodov's problem collection, number 1.154. Now, on the surface, it seems pretty straightforward, but trust me, there's a really cool twist that'll test how well we really get some of these fundamental laws of physics.
So get this. You have two identical buggies, each with an identical man on board. They're rolling towards each other. When they get right next to each other, the men jump and swap places. Now, you'd think everything would just be, well, symmetrical, right? But here's the kicker. One buggy stops dead in its tracks, while the other just keeps on going with a new velocity. How in the world is that possible? Okay, let's dive in and figure this out.
Here's how we're going to break this down. First, we'll really unpack the puzzle itself. Then, we'll figure out the right physics tool to use. From there, we'll build our first equation by looking at the whole shebang, both buggies, both men. Then, we'll get clever and build a second equation by zooming in on just one piece. After that, it's just a little algebra, and then we'll wrap up with the most important part, the strategy you can use on other problems like this.
All right, first things first. With any physics problem, you have got to be absolutely crystal clear on what's going on. So let's just make sure we all have the same mental movie playing of what happens before, during, and after the swap.
So, let's look at this in 3 stages. Before anything happens, we've got 2 units, buggy 1 with its man and buggy 2 with its man. Let's say a buggy has mass m and a man has mass m. They're heading toward each other with velocities v1 and v2. Then, during the exchange, the men jump, but they jump perpendicularly to the tracks. That detail is super important, and we'll come back to it. Finally, after the swap, buggy 1 is at a dead stop. Velocity is 0. But buggy 2 keeps on going with a new velocity we'll just call v. Our job is to figure out those original velocities, v1 and v2.
Okay, so where do we even begin? We need to reach into our physics toolkit and pull out the right principle. What fundamental law governs this kind of collision? Or, well, this kind of exchange? The problem gives us a huge hint. It says the buggies move without friction. Whenever you hear that, a light bulb should go off. It means along the direction of the rails, there are no outside forces messing with our system. And when you have an isolated system with no external forces, there's a very specific quantity that absolutely has to stay the same no matter what happens inside the system. What is it?
You got it, momentum. Remember, momentum is just mass times velocity. The law of conservation of momentum is our guiding star here. It tells us that the total momentum of our entire system, that's both buggies and both men all added up, before they jump, has to be exactly the same as the total momentum after they've swapped.
Now here's where people can get tripped up. The problem says the men jump sideways, perpendicular to the tracks. And you might be thinking, wait a minute, a jump is a force. Doesn't that mess everything up? And that is an excellent question to ask.
The key here, and this is so important, is that momentum is a vector. It has a direction. The jump is purely sideways. It has zero, and I mean zero, effect on the forward and backward motion along the rails. It's like trying to push a car forward by pushing on the side door. You're not helping. So for our analysis of the motion along the track, we can completely and safely ignore the sideways jump. It simplifies things a ton.
Okay, now that we have our principle, let's start building our first equation. And for that, we're going to define our system as literally everything involved. Both buggies and both men. The whole shebang.
So before the jump, what's the total momentum? Well, we have 2 moving things, right? First, there's buggy 1 and its man. Their combined mass is m plus m, and they're moving at velocity v1. So their momentum is just m plus m times v1. Same thing for the other guys. Buggy 2 and its man have a mass of m plus m and a velocity of v2. So their momentum is m plus m times v2.
So to get the total momentum of the whole system before the jump, we just add those 2 pieces together. This single expression you see here, P initial, represents the entire state of motion of our system at the very beginning.
Okay, now let's look at the after picture. What's the momentum after the swap? Well, we're told buggy 1, now with the new man on board, stops. Its velocity is 0, so its momentum is 0. That's easy. Buggy 2, now with its new man, is moving along with that final velocity, v. Its mass is still m plus m, so its momentum is just m plus m times v.
Now for the fun part. The law says the initial momentum has to equal the final momentum. So we just set our 2 big expressions equal to each other. And look at this. The m plus m term is in every single piece, so we can just divide it out and cancel it. What we're left with is this beautiful, simple little equation.
V1 plus V2 equals V. That's our equation 1, but we've got a problem. We have one equation, but we have two things we don't know, V1 and V2. We need to find another relationship.
So to get that second equation, we have to get a little bit creative. The trick is to change our perspective and redefine what we're looking at as our system. This is a super common spot to get stuck in physics. You use a big conservation law on the whole system, and you're still short on equations. So what do? Well, the answer is usually to zoom in and apply that same law to a smaller part of the action.
So let's try this. This is the clever move. Instead of looking at everything, let's just focus on the two components that end up together on the stopped buggy. That is, buggy 1 itself and the man who started on buggy 2 and jumped over. Let's track the momentum of just those two objects through the whole process.
Okay, let's walk through this slowly. Before the jump, what was the momentum of these two specific things? Well, buggy 1 had a mass m and a velocity v1, so its momentum was m times v1. The man who was about to land on it was on buggy 2, moving at velocity v2. His mass is m, so his momentum was m times v2. So the total starting momentum of this little subsystem is mv1 plus mv2. Now, what's their final momentum? Well, they end up together on buggy 1, which we know is stopped, so their final velocity is 0, which means their final momentum is also 0. And because momentum is conserved, the initial has to equal the final. So mv1 plus mv2 must equal 0. And just like that, we have equation 2. And here we go. This is the best part. All the hard physics thinking is done. We have two equations, two unknowns. Now it's just a bit of algebra to bring it home. So here are two puzzle pieces side by side. Equation 1, v1 plus v2 equals v. And equation 2, mv1 plus mv2 equals 0. We've got everything we need right here. Now we just need to solve this system of equations. So how do we solve it? Well, you could take equation 2 and solve for, say, v2 in terms of v1. Then you plug that into equation 1 and solve for v1. Once you have v1, you can plug it back in to find v2. When you do all that algebra, you get the answers you see right here. And take a look at v1. It's negative. Does that make sense? Of course it does. The buggies were moving toward each other, so if v2 is positive, v1 has to be negative. The math confirms what we already knew physically. It's always a good sign when that happens.
So let's step back. What did we really learn here? The answer to this specific problem is cool, but what's way more valuable is the method we use to get there, a strategy you can put in your toolkit for all sorts of other problems.
This 5-step process is a real powerhouse for mechanics problems. 1. Clearly define your system. 2. Figure out what's conserved. Here, it was momentum. 3. Apply that law to the biggest system you can. 4. And this was the key trick today. If you're stuck, cleverly redefine your system and apply the law again to a smaller piece. And 5. Just solve the math. This gives you a reliable plan of attack, so you're not just staring at a blank page, wondering where to start. And that's really how you break down a seemingly complicated puzzle into manageable chunks. So, I'll leave you with a final thought to chew on. Our whole problem was based on the men being identical. What would happen if they weren't? What if the man jumping onto buggy 1 was way heavier than the man who jumped off? Could buggy 1 still stop? Or could it even get pushed backwards? Think about how our equations would change. Thanks for joining this explainer.